Okay, so we're going to continue with our discussion of models, and I want to demonstrate a new another technique that we can use to make it easier to figure out a model. So, okay, let's first do our negation thing. So remember, we want to make all these sentences, well, we want to make the premise true and we want to make the conclusion false, but that means we want to make the negation of the conclusion true. So the negation of the conclusion is this. The negation has to be the negation of the whole thing. It's not that. That's not the negation of the conclusion. The conclusion is a disjunction, and so we have to negate the whole disjunction. Okay, so what theorem do we have that applies here? We have dm. So that means really we have the negation of, so we have put the negation on each of the components and flip the disjunction into a negation. Now then we can apply Qn on both of these because Qn is an equivalence rule. And Qn lets us move the negation across the quantifier. So we want to make both of these true. So we want this, everything is f or g, and we want this conjunction to be true. So really we want, these are the things that we want to be true. Okay, so something is not f, something is not g, but everything is either f or g. So let's go for two things in the universe. Now, you might not be sure. You might think, okay, I see what to do, but you might not. So one thing you could do is do what's called an expansion. So this thing, for all x, fx, or gx, this is not equivalent in general to any quantifier-free formula. But if there are only two things, actually, let's look at this one first. So none of these are equivalent to, in general, to a quantifier-free formula. But if we know which things there are, and there are only finitely many things, then we can come up with a quantifier-free formula that is equivalent to the quantified formula. So what is it? Well, so see this button expand down here. If we click expand, we get this thing. Now this is a little bit odd. What does this mean? So I0, this means this means we have a variable that's referring to 0. I1, this is a variable that's referring to 1. So what this says is sum x not fx. This is true in this universe, where in this model, where or in the universe like this, where there's 0 and 1, these two sentences are equivalent. So something is not f, that's equivalent to either 0 is not f or 1 is not f. And that should make sense, right? If there's something isn't f, well then either 0, one of the things is not f, and that means that either 0 or 1 isn't f, because those are the only two things that there are. So one of them has to be the thing that's not a frog, or a thing that's not a frog. And if either of these are true, if 0 is not a frog or 1 is not a frog, then there's something that's not a frog. So in a universe of size 2, these two sentences are equivalent. So what we want to do is make this true, so we can actually not even worry about that anymore. And we can do the same thing here. So when you highlight something, a formula, and you click expand, then it turns it into the quantifier-free formula, a formula that, given this universe, is equivalent to the quantified formula. And we can do the same thing here. Now, a universal, so existentials turn into disjunctions because they require that at least one of the things be true. So either this one is true, either this one has the property, or this one has the property, or this one has the property. Universals say everything has the property G, and so this has the property, and that has the property, and that has the property. So this turns into a conjunction. Okay? So for all x, gx turns into 0 is g and 1 is g. But it's not gx that the universal is attached to. The universal is attached to this. What the universal is saying is each thing is either f or g. So it's saying, 0 is f or g, and 1 is f or g, and if there are more things, each of them would be f or g. So what we get is this more complicated thing. This is the conjunction, the and then we say 0 is f or g, and also 1 is f or g. So it's a conjunction, so what we need to do actually is make both conjuncts true. So now we need to make all of these disjunctions true. And that's all we have to do. We make the expansions true, then we make the original sentences true. So we need to make f0 or g0 true. So okay, let's say that 0 is f. And now we've made this true. We need to make f1 or g1 true. Okay, well, let's say that well, actually, sorry. This we have an option with. So let's hold off. We could do either, and we'd be fine. But if we look at we've made f0 be true. Now we look here. This requires that either 0 be f, that 0 not be f, or that 1 not be f. So that means once we've decided that 0 is f, then we also need not f of I1, because we need this given that 0 is f. And so given that this is true, this is false. And so the only way for this disjunction to be true is for this to be true, and therefore for this to be false. So we need not fi1. So we need fi1 is false. So we need 1 is not in the extension of f. And it's not, right? But we don't want to change that. So now when we look at this, we need either 1 is in the extension of f or 1 is in the extension of g. Well, we don't want 1 to be in the extension of f, so we better put 1 into the extension of g. So we made this true because 0 is in the extension of f. We made this true because 1 is in the extension of g. And this is currently true because this is true, because this is false, because 1 is not in the extension of f. Okay, so far, true, true, true. Good. Let's look at this one. Either this means, well, either not g0 or not g1. Well, g1 is in the extension of g, so this is true, so this is false. But fortunately, 0 is not in the extension of g, so this is false, so this is true, and so the whole disjunction is true. So each of these is true. So we should have what we want, and indeed we do. And we can think about it. Is everything f? No, because 1 is not f. Is everything g? No, because 0 is not g. So this is false, and this is false, and so the disjunction is false. On the other hand, is it the case that everything is either f or g? Yes. 0 is f, so 0 is f or g. And 1 is g, so 1 is f or g. So this is true whenever we assign to x. So this is true, but this is false. And this, by the way, shows that the universal does not distribute over the disjunction. It turns out that if this is true, then so is that, but not vice versa. This can be true without that being true. This says everything is in each thing is like this. It's in one of these two groups. But that doesn't require that everything be in the first group, and doesn't require that everything be in the second group. It just says each thing is in at least one of the groups, but they don't all have to be in the same group. And that's why this can be true, and this can be false. Each thing is in 0 is in one of the two groups, and 1 is in one of the two groups, but it's not the case that everything is in this group, and it's not the case that everything is in this group. So, I think that actually is a pretty good illustration of expansions. Let's just do one more problem to see it applied once more. Here, I think, is a one where it's particularly helpful. All right. So, we have something is f, we have something is g, we want to make those true, and we want to make this false. Well, that means we want to make this true, right? We want to make we want to make the premises true and the conclusion false to show that the argument is invalid, so we want to make the premises true. We want to make the conclusion false, so we want to make the negation of the conclusion true. With qn, that means we want to make this true, and with nb, that means we want to make this true. So these are the three things that we want to make true. Okay. So let's try, well, we can try it with one thing. So that means to make sum x fx true, we need to make sure that 0 is in the extension of f. We need to have something in the extension of f to make sum x fx true, and the only thing there is 0, so we'll put 0 in the extension of f and make f true of 0. And now we'll do the same thing with g. So now we made these two true. Is this true? Well, no. we made this true and we made this true, but we've also made the conclusion true, and that means we made this false. So this is not working. Now, but if we have a universe with only one thing, then these two have to have these extensions for this to be true, and that means this model won't work. And if we remove either 0 from the extension of f or 0 from the extension of g, we'll make one of these two false. That means we need to expand the universe. Now, by itself, that won't help, because, well, let's see why it won't help. I mean, it doesn't help. Still, these are both true, but also this is true. So let's see why that is. To see why that is, let's mess around with the expansions again. Oops. Nope. Okay, so let's expand sum x fx. We'll turn it into f0 or f1. Let's expand sum x gx. And let's expand sum x fx or not gx. All right, so we need to make this true. And we need to make this true, and we need to make this true, and then we'll make this true, and this true, and this false. Okay, so right now, f0 or f1 is true because 0 is in the extension of f, and g0 or g1 is true because 0 is in the extension of g. But now let's look down here. What this is telling us, when it says that the conclusion is true, is that this is false. So let's see why it's false. So we have f0 if and only if g0. Well, this is true, but this is also true, and so this is false. So we have a biconditional where one side is true and one side is false, so we have a false biconditional. And over here, this is false because 1 is not in the extension of f, and this is true, so this is false. Yeah? And in fact, if we wanted to, we could even write those down. So we'd say true, and then we'd say true, but that means false, so false. Let's move this t back a little bit. Now, this is false because 1 is not in the extension of f. This is true. Nope, sorry, this is false because 1 is not in the extension of g, but that means the negation is true, so that means we have a biconditional with one side is false and one side is true. So this is not good. Right, so both biconditionals are false, and so the disjunction is also false, and that's a problem. So we need to make one of these we don't care which one, but we need to make one of the biconditionals true. So let's just make the left biconditional true. Or let's if we don't know, it doesn't matter which one is true. If either is true, the disjunction is true. And we don't have reason to care about which one is true. So let's try to make this one true. So let's leave f0 alone, and let's make the negation true. If the biconditional is true, that means this negation has to have the same truth value as the left side. They both have to be true. That means this has to be false. And that means that we need to take 0 out of the extension of g. So we're going to say we want 0 in f, and we want 1 not, and we want 0 not in g. That's going to make this true, and this false, so this true, so this is true, and this is true, so the biconditional is true, so the disjunction is true. And since 0 is in the extension of f, this is true too, so good. Now all we need to do, and if we check it, we say good, we made this true, and we made this false, which means we made this true. But the last premise is the second premise is false. This is currently false. So we want to make this premise true. Okay, well, we need to make the disjunction true, so we need to make either this true or this true. Well, if we put 0 in the extension of g, we don't want to put 0 back in the extension of g. We've decided we want 0 not to be an extension of g to keep the biconditional true and to keep the disjunction true. But that's okay. We can just make the other disjunct true. So that's what we'll do. So now 0 is f. This disjunction is true. 1 is g. So this disjunction is true because that's true. And this is 0 is f, so this is true. And 0 is not g, so this is true. So the biconditional is true. So the disjunction is true. This should work. And it does. So we're good to go. And so these expansions can help us in thinking about what is required for the different premises to be true and false. Okay, so that's what we need. We're good to go with expansions. So you can try using expansions in the invalidity problems that you have due for your next homework, or you can just try to read the quantifications directly. That's perfectly possible. If you're comfortable doing that, great. But if not, try using the expansions. I highly recommend, however, the negation thing. So you remember you want to make true, true, false, but that means you want to make not this true, and then put the negation on, and then move it in. Don't just put the negation on. That doesn't help you. You need to do both. Put the negation on, and then move it in. So good luck with your models and your invalidity problem.